Good news, everyone! Today we'll be ending naming for a while. Three's enough. Let's get started. I have a video to watch. There might be some information worth gathering in here. So I'm going to hit play. Huh. Well, that's interesting. So ammonium chloride. Showed in the video, they're NH4Cl, aqueous. And when you dissolve it in water, it's soluble. There was conductivity. That's the way that worked. Electricity went down one wire, up the other, and when the connection was made, you got light, which means conductivity. But on the periodic table, there's no element ammonium. This ammonium must be, it's ammonium chloride, so I guess this is the ammonium. It looks similar to ammonia. There's this ium at the end, and we said before that ium means cation. But we have a problem. So this compound, it looks like an ionic compound. It's solid, it's soluble, and when you dissolve it in water, the solution conducts electricity. But we also know that ionic compounds contain a metal and a nonmetal, an element that lost electrons and an element that gained electrons. There's no metal here. So how is it an ionic compound? Turns out there's a separate class of ions called polyatomic, many atoms, but it all functions as one collective unit, but it has a charge, so it's an ion. So it's a polyatomic ion. Instead of one particle, one atom with a charge, it's a group of atoms. It's still one particle with a charge. Good news for this course, everything you need to know about Table E for the regions, you have the Table E that you can use. It's selected polyatomic ions. It is not an all-inclusive list of polyatomic ions. Their names are right there. It's there. You always have it. There's a link above my head. Please use it. Table E, very important. Some things I can grab from Table E, though. Looking at the information, so I see one thing is that we've got only positive ions up here, and it does seem like the ium positive is carried through, except for mercury, because, well, if you go back to the Latin root, it's there, or Greek, or whatever it is. Another thing we can see is that there are a couple of ides present. I think there's one more right there. But otherwise, it seems like all of these have a different ending than we've seen before, which is a really good way to spot a polyatomic ion as present when you have the name. Anytime they end with ate or ite, That is the vast majority of things on this table either end in ate or ite. But you can also see that each of these contains multiple elements together, but they all do have these charges at the top. So it's got all the things that make it an ion except one extra new thing. The good news is all the things that make it an ion except the new thing, that means that there's not much to change from the old stuff that we've already talked about. You treat the whole thing as a unit in the chemical formula. So instead of saying calcium chloride, CaCl2, calcium nitrate is CaNO3 taken twice. You can imagine how hard this would be if you tried to write this. Right? Is this supposed to mean 32 oxygens and 1 nitrogen? How many? What's going on here? Well, that's why we need these parentheses. The idea here is that this 2 distributes onto both the oxygen and the nitrogen. So this is 1 calcium, 2 nitrogens, and 6 oxygens. But the way the polyatomic ion works, the better way to think of it is that you've got your calcium ion, and then you've got like this NO3 thing, and it's one thing hopping around, and it's got a negative charge, and those 4 atoms are all stuck together. Obviously, you'd have 2 of them because, that's the chemical formula there, so your ratio is 1 to 2. I know you can look at a ratio of calcium to nitrogen to oxygen, but it's probably better if you think of it as a ratio of calciums to nitrates. And again, that 8 there is that big indicator that you should be using table E on the reference table. So I wanted to bring this all together and just go through the same process as before. The only big difference is that the name ends with a different suffix sometimes, and the chemical formula now has 3 or more elements in it. So same deal, just with parentheses sometimes. Let's go through the process again. Let's figure out this compound. We've got sodium with a +1. Sulfate, we look on table E. It's SO4 with a 2- charge. So we can do the swap rule. Charge of the cation, charge of the anion. Oh, it's 1+ and 2-. And this is not a molecule because still haven't fixed the image. The number, well, we don't know that yet, and we don't know that yet, so we're not going to check. But we do know the swap rule, where the 1 goes down there and the 2 goes down there. Oh, wait. There's already a 4 there, right? Well, no, that's okay. So there's 2 things we can do about this. One, since it's a 1, we can kind of just ignore it, and we can write Na2SO4. If you wanted to include that 1 because you want to make sure you're not forgetting anything, you could put the SO4 in parentheses and put a 1 after it, like we saw previously with the calcium nitrate. You're never wrong for putting that parentheses there. I've also seen it before that sometimes it'll be written like this. All of these are correct. They're different levels of redundant, but they're correct. So we've got our numbers here. We've got 2, and it's not atoms, it's ions. I should fix that in the last one. And there's 1 of the polyatomic ions here for a total -2 charge, +2, so 0. We did this correctly. Sodium sulfate, Na2SO4. And you can do the same thing backwards. And yes, it does actually work out that you could include some stock system naming with this too. So we've got the 3 different tiers of naming all together, all at once. This is why practice makes perfect. So same deal, iron 3 hydroxide. That means iron. We're taking the 3+ charge of the 2 options, and hydroxide is OH-. We can put the 1 there for the swapping. The numbers go down there. And we're not going to write FeOH3 because this would mean 1 iron, 1 oxygen, and 3 H's. And that's not what we want to say. What we want to say is 3 hydroxides. So we need the parentheses. So this is no bueno, sad day. Instead, you're going to put the parentheses around there. This is the correct formula for iron hydroxide. Really quick, I can fill this in. 1, 3, +3, -3, 0. Not a molecule. Ion. Excellent. So same deal here. I just wanted to throw in some examples of what would happen when parentheses got involved. Here we want to come up with the name. We could unswap this to figure out what's going on. I see barium only has 1 option and chlorate only has 1 option. So we've got 2+, 1-, 2, 1, +2, -2, 0. So everything still works out the way it should. And in naming it, we've got our ion here, barium, and chlorate. And I think we can just name them as they are because since barium's not in that transition metal or post-transition metal group, we just name what's there without Roman numerals. This is barium chlorate. Simple as that. And then one final one to really just make sure we encompass all of the possible examples that might happen. Okay, we want to figure this out. We've got tin. I see 2 charges, so we're going to have to use a Roman numeral. This thing called thiosulfate. Here, when we unswap, we're not going to take the 3. That's not really, that's not a good idea. And this is where a lot of problems are going to happen. Remember that once you see more than 2 elements in your ionic compound, at least one metal, or maybe sometimes you just have to check for existence of things on table E, which this is from table E. You can also imagine that there's a 1 outside that we're going to drag back. So you might want to say SN with a plus charge and S2O3 with a minus charge. Well, 2 problems with that. 1, I see here that thiosulfate has a -2 charge, and 2, I see here that I've got 2 options for tin. So we're going to we're going to write this down. We've got a 2- charge. There's 1 of them. That's a total of -2. We have to have 0. That means this has to be a +2. I only see 1 tin in the formula, so doing our math backwards, this has to be a 2+ charge. So we actually have to double both of these. This was one of the cases where where a reduction, a simplification of the ratio took place. So now we know that our compound is tin 2 thiosulfate. I think over the course of the years you get more experience with these compounds. Right now they're just words, but eventually you'll start getting some familiarity as we work with them. Thiosulfate looks a lot like sulfate, where sulfate was SO4, 2-. Thiosulfate is S2O3, so it's like 1 fewer oxygen and 1 more sulfur. And that typically is what the prefix thio in your ion means. It means a sulfur atom is there where there wasn't one before. You can also see that in the you can see it here. This is thiocyanate and this is cyanide, so it's like cyanide with the S, right? The thio works its way in there. But that's about it when it comes to polyatomic ions. We just need practice and exposure, and then your familiarity will grow. But there are many, and they vary in charge, and they vary in number of atoms, and there aren't really a lot of hard and fast rules with how they work. They might end with 8 and 8. Usually they do, but some don't, and some of them may include metals, but a lot don't. So this question of like what constitutes an ionic compound, yes, you're looking for some metals and some nonmetals, usually. That said, if you see something that ends in 8 or 8, look at table E, it's right there, and then follow all your naming rules like before. So just to sum things up, here's your example of ammonium and chloride, and then we swap them and we get NH4Cl, an ionic compound that contains no metals. And then to unswap this, we can play this game again. Remember, there's an unspoken 1 here, so we've got copper plus and a Cr2O7 2-. So this compound would be copper 1 dichromate. And here are your examples where you have ionic compounds that are either simple binary, like calcium chloride, sodium chloride, some that use the stock system, some that use polyatomic ions. However, the rules might vary slightly between them, but they are all considered ionic, whatever makes them ionic. There has been a transfer of electrons to make this. Thanks for watching.